R.Jack from Cambridge University, who is going to talk about deviation and optimism. Thanks a lot for coming.
Well, thank you. It's great to be here. I was trying to work out when I was here before, and I couldn't remember when it was, but it's a great pleasure to be back anyway. So I'm going to talk about things which are quite simple, but I think nevertheless they are quite interesting. So my intuition and our intuition was wrong on several occasions when we were working these things out. So I thought I would just tell you about it, and if you think it's too simple, well, you can just say it's too simple, and if you think it's interesting, you can say it's interesting. So just thanks to a few people before starting. So the models I'm going to talk about, at least for the growing part, come from Steve Whitelem and Katie Klimko from Berkeley Lab, and everything kind of started for me with their models and their results, and some of them I didn't quite agree with, and some of them I did, and I think we kind of have a clearer picture now of the questions, which they were the people who posed the questions at the beginning about these fluctuations in these models and what they are like. And also Juan Garajan, I've worked with a lot on this large deviation business, so I discussed with him also these growing systems. So these two, these are for the growing systems, and then now we have something ongoing, kind of building up on these things, with Rosemary Harris from Queen Mary in London, who you might know, who's done quite a lot of work on large deviations in non-Markovian systems. Okay, so what's the story? So I'll just talk about fluctuations in simple, very, very simple models of growing clusters. You have a cluster of particles, red and blue, and it's growing according to some rule, and the rule is stochastic, so there are fluctuations, and the question is, what are the fluctuations like? So that will be the first part, and then I'll make some connection to these calculations to kind of other work which has been going on large deviations in deviations from ergodicity in stochastic models. So I'll talk about this without the motivation from ergodicity, because you'll see that it's a bit different, but hopefully that connection will become clear. And then this will be some context in order to discuss a few other simple models at the end. For example, the elephant random walk, if you know what the elephant random walk is. Turns out that's connected to these growth models, and that's what I'll talk about at the end. Okay, so that's kind of what you should have in mind. So the main part, at least the first main part, will be just this description of these fluctuations, including large fluctuations in these growing models. So just to have a picture and some motivation in our head, I'm not going to talk about these systems, but these are the kind of systems that we are interested in maybe. So what's happening here is that there are red particles and blue particles, and what's going to happen is that a cluster of red and blue particles is going to grow from the left. There's going to be a growth front here, and as it grows, it can choose whether to recruit particles of the same color as itself or to recruit particles of the opposite color. And here are some pictures of kind of final outcomes in a 3D model and a 2D model. And the only thing that's different, so these, I'm going to show movies in a minute, the only thing that's different between these four movies is somehow a parameter in the model which controls the rate at which this interface moves to the right. So what you're going to see is that when the interface goes fast, it tends to demix. When the interface goes slow, it tends to stay all blue. And in between, there seems like there's some large fluctuation regime with large domains. And so I think it's an interesting general question, which as far as I know is not really well controlled and understood, is to predict the demixing fluctuations in these systems as they grow. It's not as simple as a ferromagnet, because once it's frozen in behind the front, it's frozen as a snapshot. So there's no dynamics in the bulk, there's only interfacial dynamics. So this movie comes from this paper, and this also. And so we are interested in these kinds of general questions. And this was work done by Steve and his postdoc, Tom Haxton, and Jeremy Schmidt, who went to Kansas, and then I'm not sure where he went after that. But they were really thinking about simple models of growth inspired by experiments on DNA and whatever, but this is like a simple physicist model for growth, if you want. And from there, they realized that this was already complicated enough, but what about mean field? So what about mean field theory for that process which I just showed? Well, we should be able to do that, right? It doesn't sound like it's very complicated. So let's consider the following mean field model. So we have a cluster of particles, some of which are red and some of which are blue, and the cluster is going to grow, and the particles are just going to be added one at a time. No particles are ever going to leave, so they just get added one at a time. And the cluster is well mixed. And what that means is the cluster is fully described by two numbers, which are the number of particles, and the composition, which is just the number of red minus the number of blue over k. So the composition is between -1 and 1, and k is growing one at a time. And if the cluster is mostly red, in a sense I'm going to explain in just 1 minute, if the cluster is mostly red, it tends to recruit more red, and if it's mostly blue, it tends to recruit more blue. And this looks like magnetization, this looks like ferromagnetic coupling. You already kind of imagine what's going to happen is there's going to be a demixing transition in this model. So that's the model. No, everything is fully well mixed. So just literally just mean field, right? So really simplest possible thing. That's why I say very simple, but it was already complicated, So specifically on step k, we have k particles and the composition mk, and then we add a red particle with this probability and a blue particle with this probability, and these are just, if you think in terms of Boltzmann factors, these are just the most naive things that you would write. But there is no detailed balance here in the sense that you never unbind, you only bind. And the first particle, you just pick in red and blue with probability 1/2. And then you say, well, what happens? So there's nothing about space anywhere. So if you know your probabilistic models of growth and such things, you might recognize this as some flavor of a Polya-Ern model. And indeed it is, although that wasn't realized at the time when people started looking at this model as a model of growth. So in this paper they discussed this model, and they also discussed another model where particles arrive and they leave, but on average it grows. And what they said was the phenomenology is very much the same. So the phenomenology where you add and remove, as long as you're growing at finite rate, the phenomenology is very much the same as this model, except that it can be a little bit richer. But at least for the simple cases, the fact that this is irreversible is not essential here. That's the only reason I bring it up.
With which parameters you precisely reduce it to the Polya?
So there's the original Polya-Ern, and then there are these classes like the linear Polya-Ern of Bagchi-Pao, and there are whole families of these Polya-Erns. And this is one of the family of, it's one of the simplest families, right? There is HLS, and then there is a simpler, this is not the linear ones, it's not Bagchi-Pao, but I think it's within HLS, whatever HLS is, I forgot who these people are, I'm sorry. Hill, somebody. I think the simplest Polya is more like the elephant, which I can come back to at the end. Does that answer your question? I'm not sure.
For example, Polya, there's very striking, simple but striking thing that the outcome fraction of red and blue is actually really totally uniformly distributed, totally random.
Yes, that's right. So I think the strict Polya is something like start with a 1 red and 1 blue,
That's right. Yeah.
and then
Pick up one of them, and if it's red, you add another red.
exactly.
Return it back and add another.
So it's reinforced with probability 1.
Yeah.
So you pick one out and you always do the same.
Yeah.
So what I'll do later is the elephant, it's called, where you pick one out and then you do the same with probability p and you do the opposite with probability 1 minus p. And it's exactly the Polya is the very special, like the critical case if you want. And these are going to be the non-critical cases. These are going to be it's going to be much more regular than the Polya, which is huge fluctuation. Yes. Yeah. That's the model. So okay, just very trivial facts. So for j equals 0, you just add particles with random colors, and then you just end up with a binomial distribution with parameter 1/2 for the composition. And so there's a small standard deviation. So basically the magnetization converges for large k onto 1/2 or 0. Magnetization converges onto 0 at large times if there's no coupling. But for j bigger than 1, there is this demixing transition. So one typically finds either that mk converges to some m star, or it converges to minus m star with equal probability because the model is fully symmetric. So this is just my picture of what happens. So for j bigger than 1, you see this sort of classical ferromagnetic symmetry breaking transition, which I'm going to call here demixing. So maybe it's obvious to you already why that is, but just to help to make it more obvious. So this slide is only for intuition, because you can't trust normal, friendly, stochastic differential equations to give you the right answer for these models. So this is a sort of formal stochastic differential equation which at least behaves similarly to what I'm talking about, but you shouldn't imagine that this is a strict STE Langevin which represents the growth model. But let's suppose that if you just say, if I was going to write a Langevin, what I'd do is I'd take the mean increment in the number of red minus the number of blues, and I'd put it here, and then I'd take the variance of the increment, and I'd put it here, and then I'd say, well, first 2 moments is probably enough to describe my process by some sort of Van Kampen type expansion. I'll just stop at second order, and I would end up with an equation like this, because the mean changing in the number is given by this tanh just from the previous page. So then if we want to consider the composition, we have to divide this number by, I'm calling it time now, before I was calling it k, but it doesn't matter. So if I divide by the total number of particles, then we just get immediately to here, so just product rule, right? So we get this extra minus mt from regression to the mean, basically, so that's where it comes from. And so then you see immediately that the fixed points of this, if we assume the noise gets weak at long times, because adding one particle to a cluster of 1,000 particles doesn't make much difference to the total magnetization. So if you assume the noise is weak at long times, you expect the fixed point to solve this. And this is what you know, very familiar from ferromagnetic Ising. So that's why the transition is at j equals 1, and you can get m star from solving this equation, and everything is very simple. But there is one thing, which is this 1 over t is here. So from this you see that not only, well, I made some loose argument that the noise is getting weak at long time, but what this 1 over t is telling you is that the dynamics also gets very slow at long time. And that's again for the reason that if you add one particle to a cluster of 1,000 particles, you don't make much change to the average. So as time runs longer and longer, everything gets slower and slower. So then it turns out that the natural time unit in this problem is really log time. So this already gives you a hint for why things are going to be a bit weird, is that you can get rid of this 1 over t by changing variables to log time, and end up with sort of a nice, sensible, deterministic part of your equation, plus a noise which, if it was Gaussian, would be vanishing exponentially fast in log time. So this is not, if you just assume this equation is true, you can make predictions which are quite accurate for this model. But I think there are good reasons why you shouldn't assume this is true. Okay. So that's the story of the model and the fixed points and the mean behavior. So that's the, let's be brave and call it a phase diagram. It's not much of a phase diagram, but anyway, there's this one parameter, there's a mixed phase and a demixed phase, there's some sort of critical point, and models with reversible growth, that is particles added and removed, do the same. But this is only telling me about the typical behavior of decomposition at large times. So in this regime, at large times, the composition converges to 0 with probability 1, and over here it converges to either plus m star with probability 1/2 and minus m star with probability minus 1/2. But what about the variance, and what about large deviations, for example? So, for example, if I work in the regime where it should be demixed, occasionally I see a cluster which is not fully demixed. What's the probability of that? And similarly, if I work in the yellow regime where everything should be mixed, I occasionally see things that are not symmetrical, of course, sometimes. And can I assign a probability to the rare events where the cluster is demixed? And related, because responses are always related to fluctuations, how should I expect the response of this system to behave if I make interesting modifications to that dynamic? So of course, the first question beyond the typical behavior would be some sort of central limit theorem, and then beyond that would be some kind of large deviation theory for rare events where the system doesn't do the typical thing. And these two questions are both addressed in these two papers. So these guys were the first people to really ask the questions, and my answers to some of them are in that paper, some of which I'll talk about now. Okay, so is that clear? So it's a very simple model, but we want to understand its fluctuations. Okay, so let's just, first thing to do is just either run some trajectories or steal some trajectories from somebody else's paper. So here are some trajectories of the magnetization of the composition. These are clusters which are growing to a size 100,000, so not too small. They all start, well, after one step, you have either a red particle or a blue particle. So you have magnetization either +1 or -1. So at time 1, you're always either here or here. And then what you see is you get fairly fast convergence to something close to some sort of -m star or m star. And you get some variance which is indeed going down as the time gets longer. And I can't remember how many sample paths there are. And this is for J1.5, so significantly beyond the critical point. So I'm not going to say anything about the critical point, by the way, although I think the critical point could be an interesting thing. So we want to understand fluctuations. So once you've made some trajectories, the second thing to do is to make some histograms. So now these are histograms, or probability densities or something, for this quantity, which is the magnetization at time k, or the composition at after k steps. And I'm just using a binning parameter epsilon just to say, if I'm in the bin of size epsilon, I'll count it as 1 and otherwise 0, normalized by the bin width, and you get this sort of histogram. And the colors are increasing trajectory length. So this is clusters of size 1,000, these are clusters of size 300,000. And what you see is that indeed, this is a different J, but it doesn't really matter. What you see is that indeed you get two sharp peaks in the probability distribution, as you would sort of expect. And then you get a trough in between where the probability is pretty small, but it's not that small, right? So this is about a 1% probability, or maybe a 0.1% probability after 300,000 steps. So these probabilities are small, but these are not super, super rare events, definitely. And then out here in the wings, out beyond the mean, beyond the typical value, I'm sorry, you can see this probability is going down very fast. So there seems to be, if you have a good eye for probability distributions, there seems to be some difference in behavior between fluctuations at intermediate m and fluctuations at large m and small m, in the sense that it's extremely steep out here, but rather weakly dependent on k in here. And just in case it was not obvious, we don't have any free energy to help us, and we don't have any Boltzmann distribution to help us, and we don't have any tools of, at least a priori, we don't have any nice tools of equilibrium statistical mechanics to help us with this problem. So maybe I should say one word about why we care about these things at all. I mean, if I think back about the original red and blue pictures, you can think about a growing crystal or a growing DNA nanostructure, whatever is your favorite thing. It's definitely growing under strongly non-equilibrium conditions when the growth rate is fast. We are very far from equilibrium. We are very far from anything where we can use a free energy. And so my usual argument is, any tools which can be useful in this realm. I mean, many of you guys have developed many tools which are useful in this realm, but I would still say they are much less widespread and of less broad applicability than everything we know from equilibrium. So this is kind of in the spirit of developing toolboxes for non-equilibrium problems and what we can do with that. Okay.
Well,
yes?
what do you predict? What is known? Transfer the value in there.
So the fixed point values, the typical values
The position of m.
of these peaks
Yeah, or there.
here. So this is just the solution of m equals tanh jm of the fixed point equation.
Okay, so this is
So this works for the fixed points. So this will predict for you these values, and the noise is indeed getting small at long times. So you do indeed converge. I mean, on the basis of this argument, which I kind of emphasized was not rigorous, on the basis of this argument, the fixed point must solve this. I will partly get to it. So I would say with probability 1, mk converges to m star. So all the probability, as time gets very large, all the probability is in the peak. So just think of a central limit theorem. I mean, it's got two peaks, but think of one central limit theorem for each peak. Then the variance is going down as the cluster gets bigger. The mean is going to the same place, and you would like to imagine that it would be Gaussian about the peak, which it may or may not be. But does that answer the question at least partly?
Simple question, be sure to understand. So you said that the algebra equation that you wrote is not accurate. So the question that you are asking are not for the algebra equation, but for the...
I'm really asking for the discrete time model.
Okay. You could have asked the question about trying to compute the last deviation.
Indeed, indeed. And we did a bit of that. I mean, so the issue is that, okay, probably you guys know this better than me, but for the elephant random walk, which is not very different to this, people said at the beginning a model with Gaussian noise is going to be all right, and then later it was shown that a model with Gaussian noise is not all right, at least with additive Gaussian noise. And for large deviations, for large deviations it really matters whether you have Poisson or Gaussian. I mean, this can really come back and hurt you, and I'll say something at the end. So when I was doing it, I found writing these equations helped me a lot, and a lot of the results are the same for both. But I'm not prepared to commit as to which results are the same and which are not until I actually work it out. So certainly the level of central limit theorem or whatever would still be true. For concentration of probability, it should still be true. Yeah. Okay, so I'm going to tell you how it goes, and then I'll tell you something about why it goes like that. So there are these two regimes. There's outside the peaks and inside the peaks. And you can have in mind, if you just have in mind the simple random walk as a comparison point, the simple random walk, they all converge to 0, and there's a sharp peak at 0, because this is so for a simple random walk, this is the distance traveled divided by the time. So it converges to a Gaussian of width 1 over square root of time. So for a simple random walk, there will be one peak and it will be narrow. And then we say, well, fluctuations outside of the peak, the log probability is proportional to the number of steps with a function in front which we call the rate function. So this is an example, I mean, it's not very rigorously stated, but it's an example of a large deviation principle which basically says that the probability to see something beyond the mean is suppressed exponentially strongly in the cluster size. So I'll say something about why this is true later. But I think this is the generic behavior you should expect because you're basically adding up the colors of very many particles that you've added one at a time. So, sums of weakly dependent random variables always give you large deviation principles. But in the trough, it turns out that these fluctuations have, instead of very small probabilities, these fluctuations have moderately small probabilities in the sense that the probability to see a certain value m only scales like log k. So the log probability scales like log k. So the probability is suppressed as a power law in k instead of the probability being suppressed exponentially. And this was kind of, well, this was a bit surprising to us, although afterwards we realized it was probably, we should have known. So these are called large deviations. Apparently these are sometimes called moderate deviations, which is why I called it moderately small, but this is just jargon, I think. So why does this happen? What's going on? So, I'm going a bit slow. So, how should we analyze this? There are lots of ways. But at the moment I'm a bit of a fan of this methodology which is kind of built on optimal control theory, which you'll see is a bit like an instanton theory, but a bit more, it allows you to keep a bit more in your fluctuations than a classical instanton theory would. So we want to know about rare events. So we want to know the probability that mk, which is the cluster, the composition at step k, is within epsilon of some m. So this is a bit like the probability density for mk. I'm just using the epsilon just to hide probabilities, not densities, because otherwise, well, the peaks were very sharp, weren't they? So you can imagine the densities might start to annoy you after a while. So we'll just define this indicator function to be 1 if the event is true and 0 otherwise. So obviously the probability is just the average of the indicator function. I didn't make a typo. And then the idea is, so these are rare events, right? There are rare events that the system does something not the typical thing. So there always exists, or in these situations, there always exists an optimally controlled process for which the typical trajectories mimic the rare trajectories of the original model. So I can define a stochastic process whose typical trajectories are the trajectories that I want to know. And you can basically, in discrete time, it's a very short construction to do this. You just say, well, I'll just condition on the final point, and then I just do classical conditioning argument, and you get transition rates or transition probabilities at step k just by straightforward. I mean, in continuous time, you have to do a little bit of work, but in discrete time, it's very easy. And this seems to go by the name in the optimal control literature. This seems to be called dynamic programming. I'm not expert on these things, but this seems to be what they call it. And it's also related to these Doob transform type ideas of conditioning and whatever, which go back to people thinking about diffusions like Doob, for example. So how do we do it in real life? So we say, I've been using, have I? Well, I haven't. Let's use this bold C to denote a sample path of the dynamic, so a trajectory. I can assign a probability P to my trajectory. Actually, I really can, because it's a discrete time trajectory, so it's even easy. And then I can define an arbitrary process, which is not my process, an arbitrary controlled dynamical process in which the path probability of the controlled guy is just the path probability of the original guy multiplied by the exponential of some action type function, which just accounts for the fact that I've modified the transition rate. So whatever modification I make to the transition rates, as long as I don't do something that makes things zero where they were not zero before, I can always write a formula like this. And then the game is, then the aim is that we want to take things that we want to compute for the real process, and we just make a change of measure and express averages with respect to the original process that we understand as an average with respect to the control dynamics which we just introduced. So we just invent any model, and then we want to write this log probability in the original model in terms of quantities we can evaluate for the controlled model. And in this case, we get an inequality, because I used at some point Jensen's inequality. So the log probability of the rare event is no smaller than the log probability of the rare event in the controlled model minus something which comes from the action. So this is the average value of the action conditioned on the fact that the controlled model achieves the rare event. So this formula is completely general for any controlled model, but it's very nice because it's variational, right? So now, even if you're not smart enough to solve any equations, you can just plug things in and see if you get something nice that you like. And if you're good, then maybe you can even prove a bound from the other direction as well, and then you've really achieved something. But for the moment, we are only talking about statements of the form, this event is no rarer than this bound. So this gives me a bound on, my probability is at least as probable as this. And then the definition of the optimally controlled process from the previous page. It has three properties. First of all, it saturates this inequality. Second of all, it achieves the rare event with probability 1. And third, it mimics the rare events of interest in the original model. So if I can find a controlled process for which this inequality is an equality, and if it has this, then it is the optimally controlled process that I described on the previous page, and it mimics the rare event of interest. So this is just a very, very general way of doing rare event problems, really. But I like it at the moment. So for large deviations, this is discussed a lot in this book of Dupuy and Ellis. And for the specific growth model problem, this formula is in this paper. I didn't put, there's, I guess there would be very many books and much literature that I could put here, which I have not put, and I apologize if I should have. But yeah, there's a huge literature on this stuff, which I'm not making any attempt to summarize. Okay, so now what about large deviations? So for large deviations, this picture is going to simplify a bit. So for large deviations, this log probability, which I've just been talking about, is proportional to k, and this I of m is the rate function which I want to compute. So now what I'm going to do is divide both sides by k, and I end up just with this formula, which I just using the formula from the previous page, I get with this formula. But the point is now that I've got 1 over k here, and I've got 1 over k here, and k is going to be a large number. So if I have, for example, that this logarithm is a large number but not growing with k, then this 1 over k means that I can forget about it as k tends to infinity. So the large deviation problem, where I want to estimate the rate function of the exponential scale, is an easier problem than estimating probabilities on the linear scale, because everything which doesn't grow proportional to k I can just drop. So this large deviation situation buys me some simplicity, which is that when I divide by k I can drop a lot of terms, which I would have had to keep if I wanted a proper bound on the probability at finite time, or finite cluster size. So this object here is the conditional average of the action. So this is an indicative function, right? So this is a conditional average of the action given that I end up at m. And it also can be written as a Kullback-Leibler divergence between the control process and the original process of interest. So there's sort of information theoretic stuff behind here, but I'm not really going to use it. Okay, so that was a sort of general either reminder or very quick introduction or whatever you want to optimal control theory. Okay, so now for this model at the large deviation level of accuracy, it turns out we can get away with a lot, because if we only want to saturate this inequality, where we divide it by k on both sides, we can just take a biased random walk for our control process. And that's going to be good enough, it turns out. So we just say on step k, we'll add a red particle probability 1 plus b, and a blue particle probability 1 minus b, divide by 2. And then we are done. And that's going to be enough to saturate this inequality. On this scale, right? If I only care about probabilities on this scale. Okay, so this is just a trivial fact, right? So if I have a very large number of steps, then the composition is going to converge to the sum of the biases. And so then I can drop, if this conditional average is about 1, I can drop this, and I can treat this as just a simple average, not a conditional average. And that will help me a lot. Okay, so we're left to focus on, so because I could drop these things which were 1, this is happening with probability 1, this is happening with probability 1, so I can just replace this by the action divided by k. And then I can just write a formula now for the action, because everything's in discrete time, so you can just write formulae for all the probabilities. And you just end up with this simple looking thing. So I've replaced the sum over k by an integral, but you could have kept the sum if you prefer the sum. So an m in this formula is just the integral of b. So this is just saying that the composition at step k under the control process is just the integral of the bias up to time k. And that, therefore, this is only a function of b, which, remember, were the biases on each step. So all I have to do now is minimize this action over b subject to whatever constraints I've got, and that gives me the optimal path. And that is the optimally controlled process I'm claiming. So the log probability of the rare event is bounded below by this action. And you can write the Euler Lagrange equation, but you probably can't solve it. So at some point you probably have to do something numerical or something. But the thing maybe to emphasize at this point, if you've been looking at the large deviation literature on optimal control, is that it's absolutely essential here that the bias of the random walk depends explicitly on time. So the bias I apply at step k depends explicitly on the step. Okay. So that was the theory. Just quickly the results, because once you understand what to do, then it becomes relatively simple to solve this problem now. So on the exponential scale, which is the scale I've been kind of working on, let's think about these events where mk is 0. So let's think about trajectories which end fully demixed, even though the system typical behavior is mixed. Well, it turns out what they do is they just stay close to 0 the whole way through. So I've said to you, in principle, there's this path and all the rates depend explicitly on time and everything. In practice, for this specific case, what they do is they just stick to 0 throughout. And the reason is, if you think about this simple fixed point equation, then you know that there's stable fixed points at plus or minus m star, and there's an unstable fixed point at 0. And so what's happening here is that in order to arrive here, you just remain at the unstable fixed point for the whole trajectory. And at the unstable fixed point, there's no force driving you to be more red, and there's no force driving you to be more blue. So somehow you don't really know there's any coupling at all, actually, if you just remain in the vicinity of the unstable fixed point. And that immediately gives you that the rate function is 0. So that immediately gives you that this event here is not exponentially rare in k. In fact, it's only power law rare in k, and you can even work out how rare it is. And it's, well, I can't work out c, but I can tell you what this exponent should be. So the rate function, remember, is the probability on the exponential scale, and this probability is not exponentially rare, so the rate function is 0. The event is power law rare with an exponent roughly this. And that's because the system is poised at the unstable fixed point. So if I think about this as my kind of my quasi-free energy, this is my unstable fixed point, these are my stable fixed points. Okay, so far so good. And then the question is, what strategy would you like? What do you think are the typical trajectories like that end up here, somewhere m inside the trough? Because, well, to anticipate the answer, it's probably not a good idea to remain here for the whole trajectory because there's an enormous force pushing you down towards a stable fixed point. So those trajectories are not going to be very common at all. So what are the trajectories which give you this probability? The answer is that what they do is they sit very close to the unstable fixed point for quite a long time, and then they leave the unstable fixed point and they converge to this. So this is the stable fixed point here. This is the unstable fixed point, and this is the optimal path, or this is not the optimal path, but this is a close to optimal path. These purple ones are the ones I just described, where you sit here throughout the whole trajectory, and those ones are very rare. But these ones are much less rare. What they do is they sit somewhere near the unstable fixed point, and then they relax towards what we're calling the target, what we call the rare event value as k goes on. And if you remember, I said a long time ago now that the appropriate time coordinate in this model is log time. You can see that this relaxation back towards the target is pretty slow in this logarithmic scale. And indeed, that's a manifestation of the fact that the natural time for this model is log time and not time. So this is not the optimal path, but this is a path for which you can easily compute the action, which is a nice thing about it. So these green ones are much more likely or much less unlikely than the purple ones. And this is a graph showing how much less unlikely they are. So this is already the log probability, and this is the log probability plotted on a log scale. So, and this is for the green is for the green trajectories, the purple is for the purple trajectories. All you're supposed to see here is that the green trajectories have much lower in log probability, which means that they are much less rare. So the good strategy to arrive here, the good rare event mechanism to arrive here, is to remain near the unstable fixed point for a long time and then leave. Okay. One more thing, sorry. So this all has a flavor of an instanton calculation, but I want to make one sort of slightly more selling point for this control theory stuff, which is that these are sample paths of the control dynamics, which are good approximations to the rare event trajectories that end up here. And you can see that they are not all concentrated in one place. So I haven't just done an instanton calculation here. I am keeping a whole ensemble of paths, all of which achieve the rare event. And that's the advantage for me for the controlled process stuff over the instanton calculation, is that in principle you can keep more fluctuations. And in practice you can as well, actually. And actually what's happening in this region is not that I'm constraining it to follow the instanton. Actually what's happening in this region is I just tell it, do whatever you want. So this green dynamics here, the control process is just do the same as the original process. And then the action is strictly 0. and it just follows what I would call the natural dynamics of the model towards the target. So here what's happening is it's basically a random walk up to here, a biased random walk up to here, and then it just follows the regular dynamics of the model after that, and all the action is coming from the early part of the trajectory before this magic time. Okay. So now if you want to ask me, well, you were talking all about the exponential scale, but what about the power law scale? What about the scale where the fluctuations are really happening? If you want to get that right, you have to do a little bit more work. You really have to consider a path ensemble with quite a lot of fluctuations in it. And we don't have an absolutely sharp characterization of the optimally controlled process in this case. But I was able to compute kind of semi-analytically, let's say, by a mixture of, well, by some method, I was able to get an optimal control bound, which is shown by the purple, which is compared with the numerically exact histogram in green. And you can see that this bound is pretty good. And the way that you get this bound is you consider an optimally controlled process which simply does a random walk about the unstable fixed point up until some cutoff time k star, and then after that it does the regular dynamic. So it's essentially a delayed demixing. So you constrain it to remain near the unstable fixed point for a significant fraction of the trajectory, and then you just take off the shackles and you let it do what it wants, and you'll find that it doesn't get all the way to the fully demixed state, but instead it will give you trajectories, some of which allow you to evaluate this purple bound here. So this delayed demixing is what I'm calling it. The idea is that you remain near the unstable fixed point for a long time and then leave. Right, why does this work intuitively? Intuitively, the reason this works is that there's an incredibly strong positive feedback in this system. So the more that the system is blue, the more it wants to be blue. The more the system is red, the more it wants to be red. So the only hope to get it to do something non-typical is to kind of prevent the positive feedback kicking in. And the way to prevent the positive feedback kicking in is invest some probability at the beginning, so pay some control force cost at the beginning, and then, because the positive feedback persists for all time, because you've done this at the beginning, it'll have implications which last forever. So I think this probably has models for like wealth. This probably has implications for models of wealth creation, right? It tells you that the people who are rich already when their children will be rich forever, and that the good way to change long-term costs, long-term outcomes, a system with positive feedback is put all your investment on your children, or at nursery school, right? Teach calculus at nursery school, and you'll have a positive feedback all your life, maybe. Okay. I kind of already said this. On the large deviation scale, the biased random walk is sufficient to give you the exact rate function out here. I haven't shown the data, but out here you can get the rate function by the biased random walk. Inside we have this power law behavior. The rate function is 0. It's easy to show that. But if you want to actually estimate these probabilities, you need tighter arguments. And that's there. And after doing all this stuff, I discovered this moderately recent paper by this guy Simone Franchini, who is now working with Parisi, but before that was a mathematician in Rome. And I said that this is an urn model. So he proves a lot of results in quite a lot of generality for urns. And in particular, he identifies this strategy of starting at the unstable fixed point and diverging away as a generic feature of large deviations in urn models. But he doesn't much discuss moderate deviation. But yeah, so and this is, this paper has theorems and corollaries and is completely as rigorous as you want. Whereas everything I give here is kind of physicist argument. Okay. Never mind. Right. I want to say 3 more things in the last 5 minutes. I'll be a bit quicker. So I showed you this phase diagram, mixed, demixed, and I've talked a lot about the trough between the 2 peaks of the demixed system. So you're probably thinking, well, probably the central limit theorem holds everywhere in the yellow region and everywhere in the green region. There's only some critical point where you have diverging fluctuations and breakdown of central limit theorem. If you're thinking that, you'd be wrong, and it's more complicated. So actually, there's no central limit theorem anywhere in this shade region between 0.5 and 1.37. So in all these regimes, the fluctuations grow are larger than would be predicted by the central limit theorem, although not as large as they would be at the critical point, I guess. And in particular, we can compute the scaling of the variance with the cluster size in the grey region. It depends on some parameter alpha bigger than 1, which just depends on j. Can be computed. So there's super diffusive growth of the variance in a wide region about the critical point. And that's really coming from the fact that this is not a simple random walk, and it's not a nice, simple, self-averaging mean field model. So I'll say something a little bit more about that in a minute. There's a paper by Rosemary which also discusses similar things. And all of this behavior as well, and the trough and everything, is all true also in the model where you have addition and removal of particles, which is not a regular Earn model, although there are probably Earn models that can capture it. Okay, so this is a bit of a contrived model. I completely agree if you're thinking, well, I don't care about this model. Hopefully we can do something more general with it. So I just want to say a few words about context in which to think about these results now. So I've shown you the results for the model. How do they connect with other things that we know? And do they have implications beyond what we know? So, first of all, I've been talking a bit about large deviations at large time for the composition of a growing cluster. Maybe you know there's been a lot of work done for a long time by all of these people and more on large deviations of time averages. So the simple setup is you have some stochastic process with a configuration CT. You take a function f and you average it over some averaging time t, and then for long times the time average should converge to the ensemble average if your process is nice. And let's assume it's nice. And then we say, well, you can still have events where this convergence doesn't hold, where this f bar t doesn't converge to average f, but instead to some other value at long times. And these events have probabilities that scale with this large deviation form, where I of f is the rate function, and you can do all this in continuous time or discrete time, whatever you want. It's all the same. And so for the growth model, we would like to put the growth model into this formulation. So the easiest way to do that is to say, well, every time I add a red particle, I'll say that's f is 1. And every time I add a blue particle, I'll say that's f is minus 1. And then I'll define my mk, which was my quantity of interest, as a sort of, quotes, time average, unquotes, of this shape. And then you would say, well, I expect large deviation principle, and I should be able to just apply all the classical theory from the 70s and then the more recent theory to derive my LDP. And that was really where I started thinking about this problem from. And it turns out it doesn't really work. And the way to see it okay, let me go a bit slower. So if we were going to do the large deviation analysis for the problem I just described, we would compute this object, which is called the scaled cumulant generating function. So this is a generating function for the random variable of interest. And then we could compute the rate function by Legendre transform of the cumulant generating function. That would be the standard approach. And you can choose, always in this business, whether to get your g of lambda by a kind of spectral eigenvalue approach or by a variational kind of optimal control approach. Those two approaches are always available to you. But the point is, in all the nice cases, in all the standard large deviation cases, well, as far as I know, in the standard large deviation literature, this all works, and it works with an optimally controlled process whose rates are independent of time. So I said to you, when I do this biased random walk, I have to take time-dependent rates. But for nice ergodic processes, Markovian, homogeneous, everything nice, you can really use rates independent of time. And the reason that doesn't work in this case is that if I just consider the colors, so the probability to add red, it doesn't just depend on whether the last particle was red or blue. It depends on, in that sense, it depends on the whole history. So this model, for little m, for the composition, it's perfectly Markovian, because whether you add red or blue only depends on m. But that doesn't allow you to fit it into the structure of the problem. That doesn't allow you to fit it into the standard large deviation literature, it turns out. And you can see that it definitely doesn't, because if it did, you would end up with control rates independent of time, and you don't. So that's why this problem kind of was confusing intuitively to me for a long time. So then you might say, well, it seems like there are these non-Markovian models which somehow break down some of our understanding of large deviations and how it applies classically. Can we say something about those as well based on what we've learned? So I've taken longer than I intended, but let me just quickly tell you roughly how this goes. So the elephant random walk, I said already, on each step you pick a random step from the past and you hop in the same direction as that random step in the past with probability p, and opposite direction with probability 1 minus p. And this was proposed as the elephant random walk by Günter Schutz and Stefan Trimper 2004, I think. And then there have been a whole bunch of papers on elephant random walk, but I just mentioned this one. So this paper, they basically said this is a modified Polya-Ern, and you should be using known results for Polya-Erns to study this model. And there's a whole pile of results in this paper for this model, where they basically transfer the mathematical technology to analyze the elephant random walk. But they didn't discuss much large deviations. So again, it's called elephant. Elephant makes you think non-Markov, right? Because elephant is supposed to remember forever. That's why it's called elephant. So elephant, it's a non-Markovian random walk is how they describe it. Although if you just think about the displacement, it is actually Markov with time dependent rates. And it's very much like the growth model, except that we have a linear. It's very much like the growth model, except we have a linear law here instead of a non-linear probability here. And that means that the model's not strong enough to give you spontaneous symmetry breaking, but it does give you the breakdown of the central limit theorem in just the same way as I was just describing. And to go back to the very earlier question about the SDE, of course it's easy to invent a Gaussian version of this model where you basically take the same increments but Gaussian distributed. And you could ask, are they similar or different? Because of course for random walk it doesn't matter whether the steps are Gaussian distributed or uniform left and right. But for this model it really matters. So this is the probability to be at, so I'm calling MQ now. So Q is the position after, Q is the fraction of steps to the right after T, of T steps. And here you see the Gaussian probability distribution and the probability distribution for the real elephant. And what you see immediately is, this is in the central limit theorem regime. So what you see immediately is that the elephant random walk is not at all obeying a central limit theorem because it's not at all converging to a Gaussian. And it's known that the variance of this random variable this form is not quite right, but anyway, it scales. It's super diffusive, so it leaves the origin faster than diffusion as soon as this parameter A is bigger than a half or P is bigger than 3/4. So that's the same breakdown of the central limit theorem as I briefly advertised for the end. Okay, and then someone can ask me about this if they're interested. You can look at the instantons for the elephant, and they have quite a lot of interesting structure in them, which I'm happy to tell anybody about, but I'm not going to tell them right now. So what that leads you to is, I claim, a few moderately generic mechanisms for rare events, one of which is this delayed symmetry breaking, where you sit near an unstable fixed point and then leave it, which was also discussed by Franchini. One of which is where you make an enormous hop on the very first step and then kind of behave in a rather regular way after that. And that's what happens in the Gaussian elephant, and it also happens in a bunch of other models, and it gives you very big fluctuations in some situations. And then last is where you do something atypical for a finite fraction of the trajectory at the beginning and then exploit positive feedback to cause interesting things to happen all the way out to late times. And the examples for that are the elephant, the growth I said, and we also have an example of a very simple, admittedly, non-Markovian symmetric exclusion process which also obeys this rare event mechanism and breakdown of central limit theorem and large fluctuations at large times. Okay, I'm sorry for being a bit rushed at the end. Take-home messages maybe, well, I think these growing systems have interesting fluctuations, and it's coming from the sort of fact that the system is getting bigger, so the noise is kind of getting smaller at long times, and also there's very strong positive feedback. So there seems like there's very interesting fluctuations in there. Yes, so the long-term memory and the positive feedback is all coupling together. And I think, I don't really know what to do with this fact, but I put it to you as an interesting thing that one can expect large responses to early time perturbations in these models. And certainly when you want to construct optimal control forces to achieve some rare event at long time, you find that you should apply your control forces at early times and then exploit the positive feedback. There are examples with negative feedback where you should do exactly the opposite as well. But those have not been so much looked at least by me. Okay, thanks a lot for listening, even while it's been a little bit long, and I'm happy to have questions. I don't think it's a stupid question at all. I think with finite range memory, then you expect to be back in the more standard large deviation setting. Okay. Well, I guess I didn't really. I don't know. It's not that easy to get this kind of double peak distribution as time tends to infinity in any kind of model with short range memory. Because what will happen is you'll have a big red domain and you'll think, oh, I'm very stable in the red state, all's looking good. And then there'll be just some barrier crossing, there'll be some domain wall instanton, and suddenly it will become blue again, and it'll remain blue for a very long time. And you'll see this, alternating domains red and blue along the time axis. And you need to do something quite strong in order to prevent these whatever I'm calling them, these domain walls in time, to stop everything just self-averaging. So what, I didn't really emphasize it because I was kind of coming from the framework that it was kind of obvious that there would be a demixing from the beginning. But actually to stabilize the demixing as time tends to infinity, you do have to do a little bit of work. Whereas if you take a system like this, where here the memory really is in finite range in the sense of what's going on near the front doesn't care about what happened way back here. And in any kind of system like this, I think you do tend to get at long times eventually some domain structure like this. So I think it changes, but the nature of the crossover, everything like that, I wouldn't know.
Maybe something related to this question, but I somehow thought that those phenomena do not happen here. Once if you have Ising model in the field, the equation like that, so for instance, but if you now assume that your model is designed on a complete graph of size n, so it would be when j bigger than 1, it would be for long time, n1 n star, and then at the time which scales exponentially with that, you have a reversal and minimization becomes minus this, and then stay another exponential time there, and then another real equation, so it goes back and forth, but very large time. But in your case, because you constantly add particles, and so this 2 to the n becomes your n is growing, and it seems to me that reversals are impossible. Am I wrong?
No, I agree completely. That's exactly. So because the system's growing fast enough that the time between reversals is growing faster than the real time, I guess. So then, yeah, probably exponentially fast. So that's how it avoids. That's how it kills the. And it's important, right? Because when you see bimodal histograms and you see a trough, you think, oh, I know what to do, phase coexistence. So you think, what's the probability to see, I have two steady states, what's the probability to see something in between? Well, it should be just phase coexistence. It should be a mixture of the peaks. Should give me the probability for the trough with an interfacial cost. but that doesn't work here for exactly the reason, because everything is strongly non-equilibrium and non-stationary. The simple phase coexistence arguments don't get you this either, which, I mean, phase coexistence in time if you want. So, yeah, so that's another thing. I mean, they are very peculiar, these models.
Okay, very tiny question. You mentioned that the ends are non-Markov symmetric student process. What is the aim of that?
So what we did was, so when anybody hops to the right, you count 1, and when anybody hops to the left, you count -1. And then you divide by time to get the time averaged current. And then you take the hopping rates to depend on the time averaged current up to this time. So it's like a spatially extended version of this already. So you can, I mean, once you see what the mechanism is, you can always cook a model. But that model really brings in that this optimally controlled thing is not an instanton. I mean, the optimally controlled thing, the controlled processes that achieve the rare event, they have lots of dynamics. They are not simple, whatever you want. But you can still get the gross features, like the scaling of the variance you can get from the memory, even if you can't get any real tight results for the, at least I can't. Probably someone can.
So the particle, every particle remembers not just its own, jumps in to the right or to the left, but of everybody.
Yes, well, actually, I don't think it matters, because if it's an exclusion process, then if everybody's jumping to the right, then I'm jumping to the right. I can't make progress against the flow. So possibly for long enough times it might not matter. But that's what we do. We do mean field. But everybody's current is correlated in an exclusion process, because once you've gone round, everybody's gone round it.
So you are still emphasizing the difference between the optimal control approach and the instanton approach, which is deterministic. Optimal control is progressive. In the case of the West and the independent approach, these two are related because the whole ground state of the optimal control process is the instanton. The Jean transform. The eigenvalue is the.
Would you call it the instanton, or would you call it? I would call it like the Doob dynamics or something, but I'm not sure if I would call it. I mean, it's not. There's no path. There doesn't have to be a path concentration. Do you see?
Is there any relation in general between these two things?
I think. I think there are words. I think there are problems with words. So, if you insist that, if we insist that an instanton is concentration of probability on a single path, then I think the optimal control is always bigger, in the sense that it's a whole process, not just a single path.
Yeah, but I think also if you take the dynamics and you take the thing is going to zero, the thing of the noise.
If you take the noise to zero, but if you do the large deviation style, Donskoy-Varadhan style calculation, where you take large time,
Sure.
at finite noise.
Take large one finite time, take noise to zero, then you get.
Yes, I completely agree in that limit. But I'm not in this. Well, okay. Here I'm kind of in a hybrid of the small noise and the large time limit. But for the kind of what do we call it, Donskoy-Varadhan type large time, large deviations, then you need more than just an instanton. But in the end, it looks very similar. Right? I mean, I'm not sure if I fully answered. I mean, we could maybe discuss that. I think if you have a broad enough interpretation of instanton, you can have everything. Thanks.